the Texas Engineering Consulting House. Our project was over the FM 1187 Alito Road bridge widening. Our project directors are Justin Toney and Christian Gabriel. They work for TxDOT in the Fort Worth District. Our project location is about 32 miles west of UTA. Here's a close-up of the bridge we worked on. You can see I-20 roads directly below it. Our scope of work, we need to analyze the existing bridge and determine whether or not to replace or widen. We also need to design the superstructure and substructure parts for the deck, the girders, the bed caps, columns, abutments, and the foundation, as well as perform a bridge geometry analysis. And we also looked at preliminary cost estimate. A little bit about the background. The bridge was built in 1978, making it 37 years old. It is approximately 46 feet in width, with a length of 375 feet. There's 2 lanes with the center left-turn bay, and it has a current average annual daily traffic of 13,300 vehicles. Also has a current vertical clearance of 16 feet 5 inches. Some design challenges we had to work with geometric constraints, like vertical clearance. We didn't want to alter that. We also designed around the existing structure, and there's a 13-degree skew. We also had to consider connection details for the abutments in the deck. And a major highway, I-20, runs directly below it, so we need to consider minimizing traffic disruptions. We split the responsibilities of the design into superstructure and substructure. I worked on the deck design, Javier worked on the girder design, Christian with the bed caps and columns, Jesse with the abutments, and Alfred with foundation design and the bridge geometry analysis. Onto the bridge analysis. We considered 2 possible layouts. The first, we widen or replace, and later we considered the possibility of a twin bridge. However, we decided it was too costly, and we needed to purchase more right away, so we eliminated that option, and we stuck with widen or replace. We also considered the existing conditions. The existing TxDOT report indicated sufficiency rating of approximately 95 out of 100, meaning it is not structurally deficient, and it showed it's been reliable for 35 years. We considered constructability. A full replacement would cause more construction restraints, such as a limited right-of-way and larger traffic impact, resulting in social costs such as fuel consumption. We also considered a life cycle cost analysis. We obtained a unit price per square foot from the TxDOT website, giving us, allow us to calculate replacing now would be about $3 million, where widening would only be about $2 million. At 4% interest rate, replacement 35 years from now would be about $760,000. We chose 35 years because that is around the time the design life would end. Therefore, widening plus future replacement is still less than replacing now. So we chose to widen. Onto the deck design. My scope of work, I needed to determine the loads on the deck and design the reinforcement accordingly. I also need to consider the connection details and the header expansion joints, as well as construction alternatives. Here are the tools I use for the project. The bridge will be under normal operational use, so the limit state strength 1 and service 1 apply, giving us the load factors to the right. The dead loads I need to consider the slab, the future ACP overlay, and the T551 railing, which is the heaviest railing right away TxDOT, and the sidewalk. We also, for the live load, we use the Astro HO93, which is the heavier option of the design lane and truck or design lane in tandem. The reinforcement, I use the effective strip method and calculated the loads on a 1 foot section of the deck. Giving me, for the longitudinal reinforcement, we need number 4 bars for the top and number 5 bars for the bottom, both spaced at 9 inches. And for the transverse reinforcement, I initially designed number 5 bars for the top and bottom, spaced at 6 inches. However, to properly connect to the existing deck, I need to alter that to 5.5 inches. In order to connect to the existing structure properly, we needed to break back the deck 3 inches off of the existing girder. This gives us about 2.5 feet of exposed rebar when the required lapping distance is at 2 feet 2 inches. The existing deck is only 7.25 inch thick, where the new deck is 8.5 inches. So the rebar does not align perfectly, and in order to connect, we need to bend the rebar to connect the decks. Here's a picture of our site of the bridge. You can see there's cracking developed because of the joints. The current joints are doweled together, which is restricting movement and causing cracking in the asphalt, shown here. So we need to implement a header expansion joint, which allows movement between the deck, the slabs, and also prevents cracking for the asphalt. Some deck form alternatives: we can use a precast panel. We can also use a permanent metal formwork, which supports the concrete as it cures. And there's also the plywood formwork. However, this is outdated and it will cause more traffic interruptions. We'll now be moving on to the girder design.
Good afternoon, my name is Javier Valdez, and I will be talking to you about my girder design. The design scope for my portion was to come up with alternatives as far as girder types and the relative spacing, to assume the loading and calculate the loads on the girders, to use PG Super Analysis, which is a computer program that aids in a preliminary design for the pre-stressing strands of the girders, which still have to be confirmed with hand calculations. And these are the tools that I use. The first step in my design procedure was to calculate the live loads. I used live load loading, actual highway loading of 1993, as previously mentioned by Barry. After that, I calculated my dead loads, which include the railing, the slab, a 2-inch overlay, and a 2-inch haunch, all which sit on top of the girder. Next was to determine the vertical clearance. Now, some considerations that I have to take into account were the 8-inch losses that resulted from the new deck, the haunch, and the 2-inch cross load. Some of my options were, number 1, to keep the same actual Type 55 girder as the one currently existing. This would give me a vertical clearance of 15 feet 9 inches, which is less than what we have now. Another option was to use a TX40 girder, which is a shallower beam. This will give me a vertical clearance at the edge of the bridge of 16 feet 10 inches, but the interior existing girders were still controlled at 16.5. My next option was to use a TX46 girder, giving me a vertical clearance of 16 feet 5 inches, which is approximately the same what we have now. So the decision was made to go with TX46. Now that we have chosen a girder, we need to come up with a spacing for it. The proposed addition to each side is 20 feet. The current spacing is 6.67. But I am limited in my design by TxDOT LRFD to a half-foot overhang, to a half-foot to 4.5 foot overhang from edge of the flange, and limits my clear span to be less than 8.5 feet. So if we go with 2 TX46 girders, we'll have a center-to-center spacing of 10 feet, which is greater than the 8.5, so this design is not allowed. If we go with 4 beams, we'll have a center-to-center spacing of 4.5 with a 1 foot overhang, but this is not the most economical choice. We moved on to 3 beams at a spacing of 6.67 and a 3 foot overhang, which is very similar to what exists out in the field right now. So the decision was also made to go with this design using 3 beams. This is a profile view of FM 1187, showing from left to right that we have 3 95-foot spans, followed by 1 90-foot span. This is a typical section of the existing structure, which is 46 feet in width. This is a typical section of the proposed addition, including the 20-foot widening lane side and the new 6 TX46 girders, which will give us an overall length width of 86 feet. We have 4 spans, 6 girders per span, giving us a total of 24 new girders that will have to be fabricated. 18 of those girders are 95.5 feet long, and 6 will be 89.5 feet long. This is a typical picture of half-inch low relaxation steel, which has an ultimate strength of 270 KSI and a yield strength of 243. This is my design for the 95-foot span. We have a total of 44 low relaxation strands, 8 of which are hard. This is my design for the 90-foot spans. We have 38 low relaxation strands, 6 of which are hard. This is the shear design. I want to point out that this is only half of the beam. The other beam will be a mirror image of this. And this shows the R bars, which are the red ones, and they are number 4 bars. This is a cross-sectional view of my TX46 girder, also showing the shear reinforcement in red. One thing I want to point out about this is the hook at the top is not to carry the girder or place it in place. It is to make the deck and the girder composite so they can carry the load. And as I mentioned earlier, I had to confirm all PG super calculations by hand. As you can see, it gets very time consuming, but thanks to my PDs and my group members that gave me positive encouragement, I was able to complete this task. And we'll be moving on to band caps.
My name is Mendoza, and I was responsible for the band caps and columns. My scope includes design alternatives, cap 18 inputs and analysis, steel reinforcement, columns, and column protection. And here are the tools I used. Cap 18 is the program we use to analyze the abutment caps and vent caps, and it performs calculations on statically indeterminate continuous beams. Existing structure consists of 3 interior vent caps with 3 36-inch columns. The cap is 45 feet long along skew, 39 inches wide, and 42 inches tall. To widen the vent cap, we have 2 options. First is to extend the existing cap and tie in steel reinforcement. However, this is using small widenings and requires breaking concrete under the girders. Since this is a safety issue, we will not be using this. Another option is to use separate caps, which will result in new caps on either side of the existing. This option is safer and more economical in terms of materials used, so we'll be using this option. Cap 18 needs some information to be able to run. Textile LRFD specifies the materials and limit states used for rectangular vent caps, and a live load of HL93 for widening structures. The dead load includes components that are above the cap and the self-weight of the cap. Cap 18 also needs the geometry of the cap being designed. The cap length has to accommodate the 3 new TX46 girders and their bearing seats, which gives us a cap that is 18 feet long. This leaves a gap of about 2.75 feet, which gives the contractor enough room to form the cap. Also, since our bridge is made up of spans, TechSlot uses dowel bars that are located on the center line of bearing for the exterior girders. These are vertical bars that go into the cap, through the bearing seat and bearing pad, and into the girders. Since we're using TX46 girders, the textile LRFD specifies that we use 36-inch columns and a cap width of 42 inches. This gives us 2 3-inch gaps from the column face to the cap edge. This is used to account for errors in construction. Column spacing of 11 feet was determined by separate cap 18 iterations, with changing each iteration will have different column spacing, and we compared the moments to find which iteration gives us the lowest maximum moments. The textile LRFD states that the cap height has to be equal to or greater than the width. The existing cap is 42 inches tall, so we will use 42 inches for our new caps to match that. For aesthetic purposes, the cap taper will also try to match the existing, but will have to be reduced to 21 inches long to provide that 3-inch gap between the column face and the bottom edge of the taper. Cap 18 gives us three pieces of information that we will use for our design. First is the maximum moments, which we will use to calculate the longitudinal reinforcement. We will use 4 number 11 bars top and bottom, and 5 number 5 bars on the sides. These bars are extended throughout the length of the cap, leaving the 2.25 inch cover. There are 2 number 5 bars here shown in red that are located at the end of the cap that are used to tie to close the steel cage and help hold it together. The 1 foot 3 inch is the development length of the number 5 bar. Cap 18 also provides us our shear along different points of the cap, which we can use to design our transverse reinforcement. We have 5 number 5 stirrups and overhangs, and 9 number 5 stirrups between the columns. And lastly, Cap 18 also gives us our unfactored service loads for the foundation design. The existing columns use the textile LRFD standard ground column design for columns in multi-column vents. And there are 2 criteria that must be met to use this column design. First criteria is a column spacing between 10 and 18 feet. In our design, we use 11 feet. And the columns cannot be higher than 36 feet. Since our vertical clearance is 16 feet 5 inches, all of our columns will be below 20 feet. So our new columns can use the standard. Since our bridge is an underpass, with our columns a few feet away from the roadway, we need to consider column protection based on criteria in the AASHTO LRFP. And due to the vehicular traffic of I-20, it is deemed necessary that we need to protect the columns. What we can do is we can construct a barrier. However, this requires attenuators, and since I-20 has full depth asphalt pavement, those barriers will need drill shafts. This will result in more traffic control on I-20, and since we want to minimize traffic disruptions, we will not use the barrier. Another option is to design the column for collision using 600 kip equivalent static force mentioned in the AASHTO LRFD. However, from our vent cap design, we have 6 2-column vents, which are non-redundant structures, meaning that if a force that exceeds the standards hits the columns and causes one to fail, that section of the structure will fall. Also, since we can't change the existing columns, they will not be protected. So we cannot use this option. What we went with is a vehicle deflection wall, which is a series of 8-foot tall walls that connect each of the columns and forms a giant shear wall. This will help protect those 2-column vents and the existing columns. What it does is it redirects the force of the collision and distributes it along the length of the wall. Its design is similar to crash walls, which are used in railroads. And now onto the abutment design.
All right, I'm Geer, and I designed the abutments for this bridge. That's backwards. All right, the scope of my abutment design started with determining, actually, the load of the superstructure. Also, in the Cap 18 analysis, steel reinforcement, and connection detail alternatives. Here are the tools that I used. Now, here's the existing abutment. That's the face of it. It's 47 feet long along the skew. The wing wall is 15.5 feet long. And this is a cross-section of the cap and the back wall. Now, the textile LRFD requires us to line up the face of the back wall with the center line of the cap and the line of the drill shaft underneath it. And this is for a more structurally stable design, and also the LRFD requires us to line up the back wall, face of the back wall, and the face of the cap with the existing. Now these are the girders that are on the cap, and the dimensions of the cap, we're not able to design those until we select a girder, which Javier selected a TX46. Now we can find the dimensions of the proposed cap. This is the total widened section of our bridge. The red is existing, blue is widened. And there's a top view and a front view. This is the top of the back wall as well as the top of the wing walls and how they correspond with the front view. And this is the top of the cap in front of that back wall and how it corresponds with the front view. Now the text.lrfd, it refers to actually the bridge design guide, the bridge detailing guide. And it gives us a relationship between the length of the wing wall, the height of the back wall, the skew, and the header slope. The header slope is 3:1 ratio. It's already given in our existing plans. And with that, we can find the length of the wing wall. In this case, our wing wall is 16 foot, 6 inches that we have to design for. Now the text.lrfd, it requires any wing wall that is larger than 12 feet to have a foundation at the end of it. Now the foundation that we use is identical to the existing foundation of the existing wing wall. Is exactly what the LRT wants us to do or it requires us to do. So the existing is 18 inches in diameter and it has a 16-foot elevation into the ground. Now the location of this drill shaft is 75% down the length of that wing wall, which leaves it at 12.4 feet. Now for my Cap 18 files, the inputs that I used, first off the materials, which were required from the text.lrfd, and here are my dead loads, everything above the cap, including the cap self-weight. Here's my live loads and my states. Now for the supports, I spaced the proposed drill shafts at 10.5 feet, and they are offset from the existing drill shafts by 8 feet. So in total, we add 6 drill shafts to each abutment. This is the north abutment. For my cap results, these I used for my flexure design. And it also gives us an ultimate shear, calculations throughout the cap, along the cap, and it also gives us a maximum support reactions for the foundation design. And here's a cross-section of our cap and back wall, and this is the reinforcement, flexure reinforcement. This is the cross-section of our wing wall and the reinforcement for that, and this is the corner section of our of where the wing walls intersect with the cap and back wall. Now, all of these sections they geometrically fall within a already pre-designed text dot structure. So I use those to make it a more consistent and a more reliable design and product. Now, as I just said, the back wall, it's already a pre-designed text dot back wall that fits the geometry of it. And so that they gave us they gave us the number 5 bars at 1 foot, and the cap is actually, I designed that through the shear that the Cap 18 file gave us, and that has the number 5 bars at 6 inches. Now for the connecting into the existing abutment, we have 3 options. The first option is lapping each steel rebar, but that requires us to break back at least 9 feet into the existing abutment. This is going to require us to go under several girders, so that's pretty dangerous. We're not going to go with that. We thought of coupling as well. Coupling requires for the bars to be the same size and the same location as well, and that is not the case in the existing compared to the proposed. So our only option really was to use the dowel bars, and what you'll see here on the bottom is the dowel bars. They need to be drilled you need to drill into the existing abutment at an angle so that the steel can fully form with the epoxy that they use to connect to the existing. Now on top right here, you'll see that this is an existing abutment, and this is how we widened it. Now we're leaving the wing walls, the existing wing walls, we're leaving that decision of whether to keep them or to take them out completely. We're leaving that up to the contractor, whichever is more convenient for them. And now we have foundations.
Hello everybody, my name is Alfred and I designed the foundations for our project. So our scope began by examining a few alternatives that were available. And then went from there to examine the soil data that was given from the existing plans. Secondly, I went and received the max reactions from my Cap 18 guys. And then finally, I began my design. The tools I used were the manuals mentioned before from my teammates. But in addition, I was able to take advantage of the TxDOT Geotech manual. So some alternatives. Basically, it boiled down to two alternatives. Piling, which is more suited for softer soil, can carry a slightly higher price tag due to the scarcity of it in the DFW area. And on top of that, it would differ from the existing foundation conditions. The next alternative is drilled shaft, which is more suitable for competent in soil and hard rock. Would actually cost less because there's an abundance of drilled shaft used in the DFW area, and as well as match the existing foundation conditions. Existing soil is silty clay, followed by limestone, which is near the surface. And per the TxDOT Geotech manual states, when widening a structure that has drilled shaft, continue to use drilled shaft. So we made our choice pretty simple, drilled shaft. So I'll be designing the foundation for the abutments and the drilled shaft, the interior vent columns. It's basically just a function of the max reactions, the self-weight of the column and drill shaft, and the point bearing, as well as the skin friction if needed. This will be an allowable stress design, which differs from the LRFD method used by my teammates for their structural members. This is a TxDOT preference. And that's a picture of the actual job site with one of the drill shafts already poured and before they actually cast the abutment. So I began examining the existing soil data. What you see here is one of the soil data profile sheets, which shows me different soil layers, as well as their TCP blow counts and consolidation depths. You can see that we will be founding in limestone, which takes us to a couple of charts from the TxDOT Geotech manual, which gives us our allowable point bearing and skin friction. The allowable point bearing for this limestone will be 32 tons per square foot and applies for all the vents in this project. And for the skin friction, the same hard limestone produces a 3.2 tons per square foot skin friction value. In addition to that, the Cap 18 max reactions, which were given to me by Jesse and Christian, ended up with 133 ton and 221 ton max reaction for those members, which aided me in my next step, foundation design. So for the abutments, I used a 36-inch drill shaft with 10 number 9 bars and a number 3 spiral at a 6-inch pitch. I was able to derive a max load combining that max reaction with the self-weight of 143 tons bearing down to be offset by the allowable point bearing of 226 tons from the soil. This was more than sufficient for this load, so we can neglect the skin friction and call this an all-in bearing. Secondly, I moved on to the interior vents 2, 3, and 4. Similar design, which does match the existing, which will match the proposed column diameters of 36-inch drill shaft with 10 number 9 bars, with the R max bearing down of 234 tons and the allowable point bearing of 226 tons, necessitating a small amount of skin friction of only 8 tons. However, due to the nature of these tables that I derived these values from, the factor of safety of 2, we can basically just neglect that skin friction as it will never fully engage. Therefore, this is also an all-in bearing. I'm going to move on to the bridge geometry, which is actually a genesis point for our project. It was actually at the beginning, but To make it flow better, we moved it to the very end. This is exactly what you don't want to happen. This is not a picture of our real bridge. This is what could go wrong if you don't do proper bridge geometry. So the scope began with checking the horizontal and vertical alignments, as well as providing some key elevations and information for the haunch, and finally establishing the vertical clearance. The tools I used were the TxDOT manuals, as well as AASHTO, that we all use. But in addition to that, I took advantage of a program called BGS, which stands for Bridge Geometry System. It's basically just a program capable of performing multiple simultaneous geometric calculations for the sake of plotting bridge superstructures and providing these key detail elevations. Now, the first key detail elevation I'd like to mention are bearing seat elevations. As you can see in the picture, this is a cross-sectional cut of the widened portion with the three girders. I'm going to zoom in. What you see right there is the bearing seat. It's a very important elevation when constructing this bridge for the contractors. They need to build this bridge up to the right specific elevation in order for both ends to meet. And I was able to provide a table of finished elevations for all the bearing seats, which was provided to me by BGS. Next, you have top of column elevations, which are what they sound like, top of column. And once again, another key elevation for contractors in order to place this bridge in a precise location. And again, a table of finished elevations. Moving on to the wing wall, as mentioned by Jesse, I was also able to provide these key detail elevations, and due to the geometric skew of the bridge, these elevations were definitely going to be important for the contractors. So these XYZ points, as you see here, I was able to provide those using the BGS program. And again, another table of finished elevations for those points. And finally, to check the vertical clearance as mentioned by Javier. BGS program allowed me to perform those, or did the calculations for me with the data that I put in. And from the existing vertical clearance, we had 16 foot 5 inches. We were trying not to lose any. So, the shallower beam, thicker deck, thicker haunch, and a cross slope, we came out that our proposed vertical clearance will be approximately the exact same. So that's a very good thing. And finally, we moved on to a cost estimate for all our structural members. As mentioned earlier, we had a $2 million price tag for a preliminary estimate, which was just a very generic, not very specific cost estimate. So, what you see here are units and items and quantities and prices that I derived from the TxDOT bid tab prices. And I'll zoom in here. You can see those two things right there in particular are just the drilled shafts, the 18-inch, 30, and the 36-inch. You see their unit, the quantity, price, and finally the full amount. Bottom line, for all our structural components, it's going to be roughly 1.2 existing structure to TxDOT and AASHTO specifications. We were able to design critical connection details such as the abutment and deck, increase the user capacity on this bridge for future development, and finally gain valuable bridge design experience, which we hope will help us land the job or keep the job. We also want to give a special thanks to our project directors, Justin Tony and Christian Geer, who could not be here. We thank you very much because your help was magnificent throughout this entire process. Thank you. I also want to thank Professor Davis, all the UTA educators that filled our brains with all the knowledge that we have, and any professionals in the room that took time out of their day to come listen to us. We thank you very much. And we will end that with some question time. Thank you.
Did you consider how long the existing shafts were?
Yes, the existing shafts were on the abutments. Actually, for all the interior vents, there were 5. The existing conditions, along with the geotech manual, states that when widening that structure, you want to widen with the same method, meaning the drill shaft, but also at the same tip elevation. So it kind of made our decision for us, as well as for all the vents. So 16 feet on the north, throughout all the interior vents, 5 feet, throughout the southern abutment, only 11 feet.
Another comment I had was on, y'all mentioned the wing wall to remove or not remove.
Yes, sir.
If you don't remove it at all, it's gonna be in the way of your pavement or your approach slab.
Yes, sir.
So typically they'll knock the top of their wing walls down to get down below the pavement, okay? Also, you're widening with a shallower beam,
Yes, sir.
so your abutments, your new abutment won't line up exactly with the existing abutment when you're connecting them.
Yes.
I noticed on the connection detail, it was all lined up.
Well, then, I guess
And really, there'd be an 8-inch jump.
there would be there would actually be, it would be flush, however, we would have 5-inch bearing seats for the abutment, and the other 3 inches were absorbed by the haunch, the thicker deck, and the bearing, the last bearing cut. They're not shown, the bearing seats, but they would be built up for the abutment. Yes,
You have to ask it because you took my computer class, right?
Yes, I did.
And you were my favorite student, so can you go to your PG Super output where you show the profile of your interesting friend?
Yes.
When you do the black box, you understand what you did. For example, you made those strands inclined.
Yes, I hopped the strands.
Then why was it done?
That's done to alleviate the tension stress that develops within the beam because of the pre-stressing of the strands.
And also, did you go inject the program to see what losses you used, pre-stressing losses?
Yes, we had 10% losses.
What did you use 10%? Was it based on practice?
No, it has the long-term losses and the immediate losses. That's based on pre and such.
Good. Very useful.
Thank you.
And the photo you had of the bridge, of the overpass from the equity lanes?
Yes.
Each on equity lanes? Just wanted to point out for those of you in my class that the X number panels in the upper left corner of that sign. That is in terms of the midterm of the exit.
Just like a prison.
First of all, I want to compliment you on your alternative analysis that you did at almost every point. I thought that was really excellent. Although even though sometimes it was down to home, didn't even bother because you were constrained by some very simple rules of thumb you had to use a drill ship. But nice job. One of the better bridge projects I've seen.
Thank you. I appreciate it, thank you.
I would drive over it, yes.
Yes.
I know you posted your grade C calculations up there.
Yes, I did.
Did the rest of you at least, do some handicaps to kind of dislocate some of the results you get from these?
For myself, I did some hand calculations on the horizontal and vertical alignments, making sure that they were as built from the plan that they actually did tie. And yes, weren't as extensive, of course, maybe several sheets, but not to the extent of Javier's.
Oh, yeah. Yeah, in the abutments, yeah, I can calculate its caps, flexure, and the shear, and also for the back wall. But the back wall is it's the same as the existing almost, so we just use the tech stuff redesign.
And also a few hand calculations for the loads from the foundation to the drill shaft, just maybe 2 or 3 pages. Nothing as extensive as Javier's.
I did know what Dr. Cruz said, but also said you gotta look good, it's sharp.
Thank you. We tried our best.
Yeah.
Credit cards.
investment.
Alfred, you mentioned that the bare feet were 5 inches.
Yes, sir.
Did you consider doing anything special to them?
Yes, yes, due to the height of those bearing seats overapproaching or overpassing a certain limit, we had to consider reinforcing them. So yes, it's on our report, but we kind of, I guess, skimmed it past that part here. Yes, ma'am.
God. I was just about the weight of the sign that's strapped inside of that bridge. Was the weight of the sign included in your calculations?
No, I didn't do that.
That would probably be a heavy sign. I guess.
Guys, thank you very much.